Hi folks, welcome back. I hope you're all doing well. So I've been trying out Nix OS and the Nix package manager on one of my old machines, and I thought I'd take a quick look at a paper that goes through the design goals and some of the design and implementation of the entire Nix system. Now this paper is from back in 2004. So it's before Nix OS became a mature and somewhat popular Linux distro. And it gives a good early look at the design goals that the authors were shooting for. The overarching goal of Nix is to improve the state of software deployment. So we first have to start with what are the common big problems when it comes to software deployment as it is today. And the main problem is that most of the current mechanisms do not adequately address the issue of consistency. What do we mean by consistency? The system should behave in a way that the installation or uninstallation of a given piece of software doesn't leave the entire system in an inconsistent or broken state. This means, for example, that if you install something, all of its dependencies should also get installed. In other words, you shouldn't have an incomplete install. If you upgrade one piece of software, it should not break other pieces of software on your system. The other major goal of a good software deployment system is that it should be flexible. What the authors here mean by flexible is that it should support a wide range of software deployment policies and scenarios. So for example, it should support getting your packages from both a centralized public repository as well as maybe an internal private repository. It should support your site admin enforcing policies about packages, but also allow local users to install packages without affecting the entire system. It should be able to deploy packages both from source as well as from pre-built binaries. This is what the authors refer to when they say that the system is policy-free. What they mean is that the system itself is not imposing any of its own policies and is flexible enough to let the users and administrators define their own policies for software deployment. Nix aims to solve all these issues with traditional current software deployment mechanisms. It has a lot of features, but the main ones are that it has atomic upgrades and downgrades, and this is what really enables your system to always stay in a consistent state. It also allows you to have installation of multiple versions or multiple variants of the same software package. So you could have, for example, different versions of the Python runtime or different versions of some common library installed on the system, and things would still work okay. They would not clobber each other or mess up the users that use that library. And then another big feature of Nix is that it enables multiple user environments, which is to say that in addition to packages that are installed at the system-wide level, the user is able to not only install packages at the user level, but also construct user environments that are various subsets of all the installed packages. So going back to the central problem of existing package managers not having a good mechanism to ensure consistency, why is that? The root cause is that almost all of them work in a destructive manner, which is to say that files are copied to common system locations like /bin or /user/bin, and they could possibly overwrite files that were already there. And when you do that, you cannot guarantee consistency anymore, and you also cannot guarantee rolling back to the state before that happened. Closely related to the problem of consistency is the issue of atomicity. This refers to what happens in that time window when a new software package is being installed. If these updates are not atomic, then during the installation period, it's possible that the users of a package see an inconsistent state and hence fail. And both of these problems are related also then to the issue of identification. How exactly do you identify a specific piece of software at a specific version? If you look at all existing package managers, they might use something simple like a name followed by a version. But it is very common for just the name and the version to not be able to uniquely identify a piece of software. The authors use the example of libc here, and a given version of libc might indeed be different between different Linux distros, and it might even be different at the source level because of vendor-specific patches. Alright, so that was motivation for the Nix system as a whole and the problems in existing software deployment mechanisms that it tries to solve. So how does it do that? At the highest level, the Nix system is made up of three main components. The first one is called the Nix store, and this is where all software is installed. But importantly, packages are installed in a manner that isolates them from each other. The second major component of the Nix system is a user environment, and this is a view into the Nix store that is constructed for a particular user. And a particular user could actually have multiple user environments consisting of multiple such views. So for example, if the Nix store has both Python 2 as well as Python 3, a user could construct one environment that uses Python 2 and do some work with Python 2 in that, and then construct a totally different environment that uses Python 3. And these two would be completely isolated from each other. And the third major component, which in some sense underlies all of this, is the Nix language or Nix expressions. And this is the language in which we specify how a given software package is constructed from its constituent sources. Okay, so let's look at the Nix store in a little bit more detail. One of the fundamental problems that the Nix store tries to solve is to achieve a clean separation of what the authors call user space and installation space. Installation space is the place in the system where you're actually physically installing the software package files. And then once you have that, user space is the view into that installation space, which allows a user to use those software components. For example, on Unix, the path environment variable is a very common mechanism to construct a user space. The problem though is that the two are often not cleanly separated. In Unix, a lot of software packages are simply dumped into /user/bin because that is a standard component already included in the path environment variable. And this is one of the central design tenets of Nix, the separation between user space and installation space. Installation space is the Nix store, and user space consists of user environments that are well-defined views into the Nix store. By the way, I enjoyed this tidbit about the background behind the name Nix, which apparently comes from the Dutch word niks, which means nothing. And that refers to Nix's design principle of making every dependency explicit so that the way software is built does not see anything that has not been explicitly declared as a dependency. Now, the way you put things into the Nix store is by evaluating Nix expressions. So Nix defines its own purely functional language for manipulating sets of attributes, which are basically key value dictionaries. And this is how you define all the inputs as well as the steps for constructing a specific software component. Here we see an example for defining a Nix expression to install the Subversion software package. This part at the beginning defines all the input parameters, which includes both parameters to define options for how Subversion is built, for example, whether it should support SSL, but also includes all of Subversion's dependencies. And then when you actually want to install Subversion, you will invoke that. So this is the syntax for a function call in Nix, and provide specific values for all these input parameters. And the way Nix identifies uniquely every software component is by constructing a hash of all the inputs involved in building it. And that hash becomes part of the file name path in which that software component is installed within the Nix store. This means that different versions as well as different variants of the same software package can coexist in parallel within the Nix store without stepping on each other's toes. So you could have a different version of Subversion and its hash would be different. You could even have a different variant of Subversion, for example, one without SSL support, and it would have a different hash. And you could then uniquely identify and use each of these different variants or versions in downstream packages. And once you have this Nix store, which isolates every software package into its own directory, a lot of the other properties of the entire system fall out of that. Nix makes heavy use of symbolic links on top of the Nix store to get all these properties. So for example, a particular user environment is simply a collection of symlinks into the specific packages that the user environment wants to reference. All of those symlinks are placed into one well-known location, which is still somewhere under the Nix store, and that location is put into path. Now note that once you define your user environment to simply be a collection of symlinks into the Nix store, you can also very simply leverage that same mechanism to define versions or generations of your user environment. The way you define a new version of your environment is to construct all the symlinks that define that new environment and then switch the current link to the new version or the new generation. And the semantics of the rename system call, which is what you use to switch a symlink, guarantees that this will be an atomic operation. This means that all downstream dependencies will either always see the old set or the new set, but never both, or never some sort of inconsistent mix of the two. And once you see how the system entirely is kind of constructed as a set of nested symlinks into the Nix store, you can go back and forth between generations very easily by simply going back to a previous set of symlinks. If you've used NixOS or the Nix package manager, this will be pretty familiar to you because you can look at the packages in your path and keep following the chain of symlinks all the way back to the Nix store. Now in Nix, there is no explicit mechanism to directly delete a path from the Nix store, because if you did that, that would leave open the possibility of ending up in an inconsistent state. But what Nix does allow you to do is to garbage collect packages that are not used anymore. If you take the closure of all the packages within the store that are reachable from your user environment, that defines the set of packages that are in use, and everything else can be safely garbage collected and deleted. And Nix has utilities to let you garbage collect all your old packages to save disk space. You can in fact go one step further and even view the entire configuration of your machine as part of your software configuration. So for example, if you were defining, say, a web server machine, you would list out all the dependencies, things like Apache or Python and Perl, whatever you needed to serve up things. But in addition to that, you can even view your Apache configuration file as a component that needs to be installed. So you could in fact go ahead and define the entire configuration of that machine in a reproducible manner as a Nix expression, and then use that to stand up web servers automatically and reproducibly. In fact, this is today one of the core selling propositions of Nix OS. This ability to capture the configuration of the entire system in one config file, configuration.nix, and then be able to reproduce it across many machines. So like I said, this paper was written back in 2004, and at the time they had only about 180 packages in their package repository. Fast forward to today, and the Nix package repository is actually the biggest one in terms of number of packages among all the distros on DistroWatch. So they've come quite a long way. So that was a quick look at the design and implementation of the Nix software deployment system and how it enables consistent, flexible, and configuration-based installation of software packages, while also allowing you to atomically switch back and forth between versions of your entire configuration. So I hope you enjoyed that, and I will see you next time. Thank you very much.